let us look at merge sort. Merge sort is one of the sorting techniques which is very efficient in terms of its performance. Now, merge sort uses merge sort actually as a term merge is there. We look at this what this merge means or merging means. This merge sort uses divide and conquer approach. Now let us take the the elements here. We have 6 elements, and we have to sort these elements. So the problem to solve is sort the elements in ascending order. So I mean, mostly the term is used. Term uses non-decreasing order. It's nothing but ascending order itself. Now what merge sort does is it splits the elements into 2 subsets, just like binary search. Split the elements into 2 subsets, and these elements are non-overlapping. Again, remember, they are not overlapping. Split the elements into 2 subsets. Each set is individually sorted, and then we merge these two. When each set is individually sorted, that means we have 2 sorted sets. We merge these 2 sorted sets to get the original set, original sorted set. Now here also problem is large. We have to split that problem or divide that problem into small sub-problems and solve it. Now let us talk about the solution in terms of divide and conquer strategy. Now here 3 phases of divide and conquer is, first phase is divide. So n number of elements are divided into n by 2 elements. And here also it's divided by 2 itself, not by 3 or 4 or something. It's divided by 2. Merge sort always divides the elements into 2 subsets, divide by 2. So 2 subsets, that is what is the divide phase. Conquer phase is to sort the 2 subsets. And sorting those 2 subsets is nothing but when we have left subset and right subset, those 2 subsets may also be very large. So again, merge sort can be applied on those 2 subsets. And I mean, again, applying merge sort means we are recursively doing that. So conquer approach here is to sort the 2 subsets recursively using merge sort. Now, till when these 2 subsets, I mean, till when should we call recursively? We should call merge sort. The idea is here is that we have large collection, n number of elements. We divide those elements into subsets n by 2, such that at the end or until there is only one element remaining in the subset. And the idea of merge sort is that when there is only one element remaining in the subset, that means that element is already sorted. So that's the idea, to divide into subsets, subarrays, until there is only one element left in the subset. When there is one element left, it means that it is sorted. Then we have the last the phase as the combine. When we have 2 sorted subsets, merge those 2. So merge, the term merge is coming from combine. Combine those 2 sorted subsets to get a sorted set or sorted original set. So that's the basic idea about merge sort. Now here, actual merge sort algorithm only can be completed in 3 steps, 3 or 4 steps. That's all. But the actual part or actual working of merge sort is in the combine phase, when we merge 2 sorted subsets. So we will first look at how to merge 2 sorted subsets. And this algorithm is known as merge sort algorithm. This algorithm is known as merge algorithm. And merge sort uses this merge algorithm. So the actual working or the main computational part is in merge algorithm. Now let us take these two subsets, or we say these two arrays, 31, 57, 84 and 25, 63 and 96. Now these two subsets, they are sorted, individually sorted, not combinedly, individually sorted. 31, 57, 84 is individually sorted, 25, 63, 96 is individually sorted. Let us call this as array because element collection elements is stored in an array. Now actually, this is a single array. It's a single array. We are not taking two different arrays. This is a single array. This single array obviously is going to have its indices. Actually is divided. We say that it's divided into two parts. So here what we have is we have low index starting from first index referring to the first index. We have high index referring to the last index, and mid index computed among these two. That is 6 plus 1 plus 6, 7 by 2 is 3.5. Floor value is 3, index 3 itself. So this array, for our convenience, the elements are in sequential order. There are no two different arrays. They are sequential order. But for our convenience, let us physically have a separation between these two. Now we will call this part as left subarray, this part as right subarray. Now we will take a temporary array. So what we are trying to do is we are trying to merge these elements of the left subarray and the right subarray. To do that, we are using a temporary array known as B. This is a temporary. Now, we will have a variable h, which is pointing to low. We will have a variable I, which will point to index of 1 in the array B. Remember, it's array B. Then we will have another index as j, which points to the first element of the right subarray. It is actually index 4, but it's the first element of the right subarray. Now, the logic behind this is we compare the element at index h, which is the first element from left subarray, with the first element from right subarray. Whichever is less, we will try to store that in array B at index I. So h is first index, j is fourth index, element at index h is 31, element at index j is 25. 25 is less than 31. So 25 is stored at index I. Then which element we stored? We stored 25, which was referring by j. So this element we have stored in this array. Actually, it is not deleted. I'm just darking it so that to show that this element is completed. We have processed this element. Then j will move to the next. H is not moving, remember. So whichever element we stored in array B, the index of that element moves to the right. Then simultaneously I will be moved so that we can store the next element at index second, the next index in array B. Now again we perform the same step. Element at H, which is still the first element, is checked with element at J. Now the jth element, the second element of the right subarray. Now whichever is smaller, that element is stored at index I. And obviously 31 was stored, so we move J to the left, towards the right. Same thing happens, again I is also moved so that next element can be stored. Now element at H is compared with element at J. Which one is smaller? 57. So 57 is stored H moves to the right. Again, I also moves to the right. Again, element at H is checked with J. 63 is smaller, so 63 is stored here. And then J, since 63 was stored, J moves to the right. Again, these two are, I also moves. Again, H is compared with J. H is element at H is smaller, that is 84. So 84 is copied to array B, stored at array B, and H moves. Now when H moves, it is not the blank thing. It is from index 3 to index 4, it is moving. Now when H crosses mid-index, then we stop. Obviously I is moved, then we stop. That means when H crosses mid-index, that means all the elements of the left subarray are stored in array B. There may be some elements, or may not be some elements remaining in right index. In this case, it is remaining. It's not only one element. We can have so many other elements also remaining here. Doesn't matter. Or there may be the case that J index crosses. Or there may be the case that J index crosses high, H will be at mid, J crosses high. If J crosses high, that means there are no more elements in the right. All the elements of right subarray is stored in array B. There may be elements left in the left subarray. But in this case, it's the right subarray. So what happens is, at I, from I we try to store all the elements from J till end. Now it's only one element, so this is nothing, just storing that element itself. If there are other elements, then I is moved, J is also moved, then J goes and all the other elements will be stored in array B. So this is how merge sort happens. This is how merging happens, not merge sort, merging happens. Now, once all the elements are compared and stored in the temporary array B, actually we are merging whom? Whom are we merging? Two sorted arrays. And the result of two sorted arrays is a sorted array which when we merged is stored in array B. Now we have to copy these elements back into the complete array A. So what we do is we use a variable k. We use another way, that k variable is obviously pointing to first index of array as well as first index of array B. And then each element is copied back, moving, incrementing the index k. And then these two things are merged. Actually, when we copy it, that means it is merged itself. So we have separated for our convenience, we have separated by a space, just for our convenience, but it's actually, it is the same array itself, which we have, what do we call, separated, and which we have physically separated for our convenience, but it's the same array. So now you can find that the whole array is sorted. Now just before we look at the merge sort part, let me clarify one more point here. That is the array B. What should be the size of array B? What should be the size of array B? The size of array B should be equal to the size of the left subarray as well as size of the right subarray. Now, left and right subarray is nothing but starting from low index to high index. So, the size of the array B should be till high index. That is the size of the the size of the, what do you call, temporary array B. So temporary arrays B size will be till high index. Now, as we have seen this example, let us now look at the quickly look at the algorithm. So this algorithm is called as merge. Remember, this is not merge sort. This is merge algorithm. The heart of merge sort actually. This is the merge algorithm. Merge algorithm takes three parameters: low, mid, and high. This is what three parameters: low, mid, and high. Low we pass initially 1, high we pass initially the nth element. Mid is computed using low plus high by 2. Okay. Then we have a temporary array. So what we have a temporary array, and then this merge algorithm takes a variable h which is initialized to low, variable I which is initialized to low itself, which will be pointing to array B. We'll come to this array, uh, part of array B, and then there is a j which will be initialized to mid plus 1. So mid is 3 here, mid will be 4. So whatever mid is there, j will be initialized to mid plus 1. So h will be the start index of left subarray, j will be the start index of the right subarray. Then we have a while loop to check whether h is less than mid, less than equal to mid. If h crosses mid, that means all elements are done for left subarray. And j less than high. If j crosses high, that means all the elements of right subarray are completed. Now, these two things. Now, if a of h is less than equal to a of j, if this element is less than equal to this element, then b of I, you're storing in b of I equal to a of h. This is less than this, so store this. Else, and increment, obviously, increment the h part. Else, store j, this is small, store j in b of I and increment the j part. So if element of left subarray is small, we store that in b and then increase the h index. If element of right subarray is small, we store the element of right subarray in array b and increment the right index, j index for the right subarray. Now this happens. Now, and this for once the condition is checked, obviously we have to move I also. So I is equal to I plus 1. That is, we are moving I. Now, this while loop continues till this h is less than equal to mid or j less than equal to high becomes false. Any one becomes false, that means that array is completed. And we come out of the while loop. So just let me quickly trace this one. Then you can look at the video later for tracing part. Now, then what happens is, at the last stage, now mid has crossed h. H has crossed mid. So this condition becomes false. So while loop is not executed. And all the elements of left subarray is completed. Right subarray, there might be elements left in the left or the right subarray. So if h is greater than mid, that means h crosses mid, that means left is over. Now copy all the elements from j equal to j, we are using a for loop, j to high at the end, all the elements into the array b and increment I. Else what happens? That means else j is high, crosses j. So copy all the elements from left subarray into array b and increment the index. So once this is completed, counting remaining elements, what is left is we are left with the array B. Now this array B has sorted elements. All these sorted elements now have to be copied back into array A. So for doing that, we use a while loop. We use a for loop for k equal to low to high. So k is initially pointing to index 1. For k equal to low to high, copy all the elements from b of k, this b of k into a of k. So once this is done, we will be having the entire thing in sorted fashion. So this is how we try to merge using merge algorithm, we try to merge two sorted arrays into a larger sorted array. And this is the main merge sort part. And now we will look at the complexity of this merge sort. Sorry, merge algorithm, not merge sort, merge algorithm. Before moving further, we look at the complexity of the merge algorithm. The complexity of this merge algorithm, this is the while loop. How many times this while loop will run? It will run till h is less than equal to mid, or j is, it will run until h becomes greater than mid. That is, h is greater than mid and j is greater than high. So assume that in first subarray they are n elements. Second subarray also they are n elements. So we say n by 2, but assume at most, maximum, we call n by n itself. So this while loop will run for n times. Then in this, these are if statement, primitive statements inside, but inside if statements we have a for loop. So this for loop also may run for n times. This for loop also at most will run for n times. Then copying the elements back into array also runs for n times. Now remember, these are not nested loops. They are individual loops. And each one is running n times. So total it is 4n. So the polynomial or function f of n, if we say f of n equal to 4n. 4 is a constant. We can remove 4 and we can say that the time complexity of this merge algorithm is O of n. Not merge sort, merge algorithm is O of n. Now comes the next part of merge sort itself. So we have seen how to conquer, how to actually combine. We have seen how to combine, merge. Now let us look at the merge sort. Merge sort is very simple algorithm. Merge sort takes two parameters, low and high. Low is the first, initially it will be index 1, high will be index n. If low is less than high, that means problem is large. So we compute the mid index. Mid is low plus high by 2. Then we perform merge sort on low and instead of high, we pass mid. That is, we are performing merge sort on left subarray. And again successfully perform. This is not either, it is successfully. We are performing merge sort on left half of the array, left subarray. Perform merge sort on the right subarray. Instead of passing low, we pass mid plus 1. Mid plus 1 to high. High is the last index. Why are we using mid plus 1? Not mid. Here we used low equal comma mid, and instead of low we are using mid plus 1 comma high. Why are we not using mid comma high? Because the subsets or subproblems are non-overlapping. They don't overlap. So that is why from low till mid is one subarray. From mid plus 1 till high is another subarray. So that is why we have low comma mid and mid plus 1 comma high. In binary search, we made mid minus 1 and pass mid plus 1. Here we cannot use mid minus 1. If you use mid minus 1, that mid element will be left out. It will not be sorted. So that is why, since the array has to be divided, problem has to be divided into equal subproblems. That is why we are using mid and mid plus 1. Now once this merge sort is recursively called on the left subarray and right subarray, that is the conquer part, we see in divide, that is mid equal to low plus high by 2. Conquer part, we are left with combine, the merge part, combine part. So once these merge sort happens, ultimately we will call the merge. This is the merge algorithm that we have already seen, passing low, mid and high indexes as the parameters. So actual merge sort is very simple, 3 or 4 lines of algorithm. Merge sort, we can implement or accomplish merge sort, but actual thing lies in merge. That is the algorithm we have seen here in this slide, a previous slide. We have seen this algorithm. This is the heart or main computation part. And now let us look at the time complexity. Let us quickly solve the time complexity. This is the divide part. We divide it. Check this divide. We call merge sort, passing merge and mid plus 1, then performing merge. Now let us quickly look at the time complexity of this merge algorithm. Now, merge sort algorithm. Now here also we will construct the tree. If you look at this tree, what we have is low is less than equal to high. In binary search, we constructed the tree using the mid values. Here also we are trying to do the same thing. We construct the tree. Here you can find 1, 6, that is low and high. So these values are low and high values. So nodes are not having mid values but low and high values. So this is the actual, green is after performing merge. So we have 1, 6 is divided into 1, 3, 4, 6, divided into 1, 2, 3, 3. 4, 6 is divided into 4, 5, 6, 6. 1, 2 is divided into 1, 1, 2, 2. 3, 3 is as it is. There is 3, 3. Low is 3, high is 3 means there is only one element. That we have found that solution. Then 4, 5 is divided into 4, 4, 5, 5. Now, 1, 1, there is only one element, that is 31. 2, 2, there is only one element, 84. This one subset, they contain only one element, both are sorted. Merge them. That is what is the merge algorithm. Merge them. When we merge them, we get it 31, 84. Then, at this stage, 31, 84 are sorted. 3, 3, only one element, 57. So this is sorted, 1, 2, 3, 3 is sorted, so merge them. When we merge them, we get 31, 57, 84. Then, to the left side, to the right side, we have 4, 4. 4, 4 is only one element, that is 96. At index 4, we have 96. 5, 5, 63. At fifth index, we have 63. So these two are subsets with only one element. Merge them. They are already sorted. So when we merge them, we get 63, 96. Then 6, 6 is 25. Here we have 25. Merge them. Both are sorted subsets. Merge them to get a sorted set. 25, 63, 94. So at this place, we have two sorted sets. So merge these two of them. We get the result at 25, 31, 57, 63, 84 and 96. So this is how the merge sort, if you divide this, the recursive part of merge sort when it is called, the left side is completed first, then the right side is completed. And simultaneously when we are combining, we are joining and getting the result. So this is how merge sort works. Now let us look at the merge sort. Merge sort is the recurrence. It's recursive algorithm, so we need to find recurrence relation. Let us assume T of n is the time complexity for the merge sort. Assume T of n is the time complexity for the merge sort. Now, this merge sort T of n, n is the size of the array. If low is less than high, that means problem is large. And problem is, if problem is small, that means n is 1. So if n is 1, time is complexity 1 itself. It's a unit time to compute because this will be only one element in the array and you don't have to do anything, it's already sorted. Then if low is less than high, otherwise that is n greater than 1. We compute mid, it's a trivial part because it takes only unit time to compute. Then we have merge sort. This merge sort, we are dividing the array into 2. So if merge sort takes n as the input, recursively calling this merge sort at this stage, passing mid means we are dividing it by 2. So n divided by 2. So this takes T of n by 2. Then again to the right subarray, we are again calling merge sort. This also takes the rest of the half of the elements, so T of n by 2. And then we have merge. Merge we have already computed. It takes n times to compute. O of n times to compute. Now, if you compare this with binary search either gets called recursively on the left or the right. So we take T of n by 2 only once. But here we have to call the merge sort on the left as well as on the right subarray. So that is why here merge sort takes T of n by 2 and here merge sort takes T of n by 2. So if we sum up, if n is greater than or equal to 1, then if we sum up these things, we have 2Tn by 2 plus n. This is the recurrence relation. Now we will quickly solve this recurrence relation because you've already seen in the earlier stage of binary search how to compute. The only thing is we have 2 over here. Tn by 2, 2Tn by 2, there we had only Tn by 2. So we found the first equation substituting n, the first equation, the original equation itself. Second equation, n instead of n, we substitute n by 2. So it will be n by 2 plus, T of n by 2 equal to 2T of n by 4. This 2 remains as it is. This is 2. We cannot substitute anything over here. It's 2. Only in place of n, we are substituting n by 2. And here it is n, and in binary search we had 1. Here we have n. So instead of n, we substitute by n by 2. Then same way for n by 4, what happens is we have T n by 4 equal to 2T n by 4 by 2, so it becomes n by 8, n by 8 plus, instead of n, we have n by 4. That becomes our third equation. Then fourth equation is, instead of n, we are substituting n by 8. So here 2T n by 8 by 2, which is n by 16, plus, instead of n, we substitute n by 8, n by 8. So this becomes our fourth equation. Now let us successfully substitute these things. So here we have 2T n by 2 plus n. So instead of T n by 2, we are substituting 2T n by 4 plus n by 2. So 2 into 2T n by 4 plus n by 2. So what happens here is this whole thing, 2 multiplied by 2 is 4T n by 4 plus this 2 and 2 gets cancelled. So this is n plus n. So we have n plus n. Then instead of, so this whole equation, instead of Tn by 4, we will substitute it with 2Tn by 8 plus 4n by 4. So this 4 is over here 4, and instead of Tn by 4, we are substituting 2Tn by 8 plus n by 4. So what happens? This becomes 8Tn by 8, 8Tn by 8, plus this 4 and this 4 gets cancelled. So we have n itself, plus n plus n. So we have 3 n's. Same thing, it's t, instead of Tn by 8, we will substitute by 2Tn by 16 plus n by 8. So here we have 8 multiplied by 2Tn by 16 plus n by 8. So 8 gets cancelled, and this is 2T is 16. So 16Tn by 16 plus n plus n plus n plus n, successive n's. So if we compute this, if we substitute this recursively for the ith time, this is 2 power 2. Actually, this is 2 power 1, 2 power 2, 2 power 3, 2 power 4. For ith time, it will be 2 power I. Then T of n by 2 power I, because 2 power 2, 2 power 2 power 2, n by 2 power 1, n by 2 power 2, n by 2 power 3, n by 2 power 4, till n by 2 power I, plus first time n is 1, second time n is 2, third iteration, third time n is 3, fourth time n is 4, ith time n will be I multiplied by n. So we substitute for the ith time, we have this as the relation, this as the expression. Now let us solve this expression. Now this part, n by 2i, if it is equal to 1, we know that it is constant time. So when n equal to 1, the time is 1. So T of 1 means n by 2 power I should be equal to 1, which is nothing but equal to n equal to 2 power I, which is nothing but I equal to log n base 2, log n base 2. Now let us substitute these 2 power I as it is. Instead of t of n by 2 power I, we said that it becomes 1. It reduces to 1. So that we have a solution. So t of 1 is 1 itself. T of 1 we are writing. Plus I multiplied by n. Now t of 1 is 1. So 2 power I multiplied by 1 is 2 power I plus I multiplied by n. Now what is 2 power I? Because this whole expression now has to be written in terms of n, not in terms of I. The time we found it and we have reduced it. This whole thing has to be written in terms of n. So 2 power I. What is 2 power I? 2 power I is nothing but n is equal to n. So we say n plus. What is I? I is log n. So we have log n multiplied by n. So this expression becomes n plus n multiplied by log n, which is nothing but asymptotically T of n, or time complexity of merge sort, is equal to O of, actually this n log n is the highest polynomial. So the time complexity is O of n log n for merge sort. So this is what was all about merge sort. Remember, merge sort has got the time complexity in worst case as O of n log n. So this is how divide and conquer approach. Using divide and conquer strategy, we can divide the number of elements into different subsets, recursively sort those subsets, or call merge sort on that subset, and finally combine sorted subsets into one and perform the merge sort. So we have seen merge sort, how it uses divide and conquer approach. We have seen the algorithm for the merge sort as well as merge algorithm. And then using the recurrence relation, we have computed the time complexity of merge sort.